So let's get starting with the modeling. As we can see, we are going to design the following profile over here. So this will be the steel profile. We have over here the height, the length, the hard thickness over here in the middle, and the sole thickness. Now, in order to design those, within CATIA, I'm going to start with all of those within the Y and Z plane. And initially, I want to draw an axis over here. And afterwards, using the profile feature, I will roughly sketch that profile. Over here, I can add that constraint, so it will be a lot easier. And over here, I can end this directly over here. Now, using the constraint, I know that this will have 8 millimeters. The same over here. So this will be the sole thickness. We're gonna add now the middle thickness over here. So that will be 2.5 over here, so 2.5 millimeters. And we're still gonna have this to be 100 in length. And this should have 50. So this will be the profile. Now I want to select everything and I want to mirror this around the axis. And at the end, I also want to add some fillets over here. So within CATIA, they are called corners. I want to select those 4 points over here and I will choose the corner feature. And the radius, I will set this to 10. Now this will be the profile, and the profile will be padded on a length of 2000 meters. So I want in total this beam to have 2 meters. Now this will be the component. Before we're gonna do the analysis, we also need to define the material. So to do that, you see over here on the bottom, apply material. Within CATIA, we don't have a wide variety of, let's say, materials. We're mostly going to have general. For example, we're going to have the steel over here. This will be the case study that we're going to do. So I'm going to drag and drop it over here. And now within the part, we're going to see that the steel will be added. If I will double click the steel over here and I will go to analysis, we're going to see over here the density and the yield strength. So this will be the material, let's say, parameters that will influence the analysis. So you're going to see the yield strength will have the following value over here. Okay, so our part is ready for the analysis. Therefore, we can go to start, analyzing simulation, generative structure analysis. And over here, you're going to have the following notifications. So we can define a static analysis, a frequency, or a free frequency. So we are going to go for the first one. This will be the most basic. So we want to define a static analysis. Okay, so now we have over here within the tree, we're going to see that the finite element model will integrate nodes and elements. If I will expand this, we're going to have over here an octree. So this will be the mesh. If I will double click on this, we're going to see some parameters regarding this. Now, this will be the size of those meshes. So let me just go over here within this. So this was the design part that we already did. Now we're going to take a look at those octrees for the meshes. Over here I added some general information regarding that. As we can see, octree meshes. So these are a meshing technique we use within CATIA V5 to create finite element analysis models. It's particularly effective for complex geometry or when a high level of detail is required. Okay, so how does this work? We're gonna have an octree decomposition. So the geometry will be divided into smaller cubes. Those are the octants. And this process will continue until the desired level of refinement is reached. Now, within CATIA, if for example I will leave it like this with a size of 125, this is quite a large value, so I can click OK. we're gonna see that this is waiting for an update over here, but we're gonna be able to see those as soon as we're gonna do a computational. So the material is added. If I will change this, but now if I also want to visualize the octree, so how that mesh was divided into those smaller elements that will be used for the analysis, I need to define a compute over here. So I'll click OK, and now we're gonna see that all of those will be updated. I'm gonna click OK because I want this to be computed. In this case, since we don't have any constraints and we don't have any forces, we're gonna have the following error, but that shouldn't be a problem for now. Now, if I will go over here within the deformation at the top, so you're gonna find this over here within the image, we're gonna see the remesh. So this will be the octree mesh in this case. And you're gonna see that this has been split into various small triangles, and they will be used for the calculation. So over here on the sides, those will be smaller. And actually, they only have that face as a rectangle, as a triangle, sorry. But if I'm gonna leave my mouse, we're gonna see that this element will look like this. So these are the tetrahedrons over here. So we see all of those individual elements. Now, it's usually a good idea to make this smaller. For example, in this case, with those values, we see that the beam over here doesn't even follow the profile that we added. So we had over here that radius of 10, and we see that over here, during the remesh, this has been heavily deformed. But this will be actually the mesh used for the calculation. Now, if I want to go and add some elements, so over here on the deform mesh, if you're gonna want to go back to the default visualization, you can just deactivate that, and you're gonna go back to the default visualization. I will go over here for the clamp, and as a case study, I will clamp this beam over here, so just on one side. And afterwards, I will add a distributed force on the top surface. So we're gonna see the direction of the force indicated by those arrows. Over here, I have the value from my previous, so I'm just gonna add initially 5,000 newtons over here. I press tab in order to have that refresh. And on the z-axis, this should be with minus. If I will remove that, you're gonna see that the force will be located and distributed like this, but we want it to face the part. And now, since we have that constraint added over here and we have the load, we can do a computation for this. So just like before, I'll do the computation. And now we are also going to have the possibility over here. If I will click, I'm going to see a deformation. In this case, this is the mesh used for that calculus, but over here we're going to have the displacement. So if I will click on the displacement, we're going to see all of those sample points. So I can move with the mouse in order to go for each point. And over here, if I'm going to activate and deactivate that by clicking on it, I can move it. And currently we see that for that distributed force, we're going to have the following displacement. So the load over here for the distributed force was 5,000 newtons. And those will have the following displacement. So over here, onto the other side that hasn't been clamped, we're going to have a maximum value of 4.25. So yeah, we can also go over here on the bottom. We can do an image extrema, and that will give us the lowest value. So over here where the beam was clamped, we're going to see a value of 0. So that will not displace at all. But over here, the global maximum will be 4.2. So keep in mind that this is with the mesh set to 125, which is quite a lot. If I will go with something smaller, for example, I will go with 20. So this will be a lot smaller. If I will do the same computation again, And the force will remain again the same. So 5,000 newtons. I will not change this. And if I will check the displacement now, we're gonna see that now the displacement is has gone all the way up to 6.28. But now, since the mesh used for this is much more refined, if I'm gonna go over here on the deformation, you're gonna see that this will be more accurate to the shape of our final profile over here. So we can even go further, since the computational power is not that high, and we can easily go and have this remesh into smaller elements. So we see all of those elements now. If I will move my mouse, they will be a lot smaller. So let's go within the final within the mesh, and I will go with a size, for example, 4 over here, so a lot smaller. I will do the same computation again. We're gonna see that now it will take several seconds in order to have that computed, but it shouldn't be any problem. Yeah, so we have this elapsed time over here. We see for the mesh execution 16 seconds, and afterwards the other took several seconds, so 1 or 2 seconds. This is why it's important to define that properly. So usually if you're gonna go for lower values, the mesh will be divided into smaller elements and the calculation will take a lot. Just like we see now, I jump from the 126 was initially to 20 and now to 4. And now we can again see those displacement over here. So in this case, we see the value for the displacement. This went all the way to 6.71. So it didn't go that far from the previous result, even though the mesh now is a lot smoother. And we're also gonna see now the profile of the beam. If we're gonna take a look over here, we're gonna see the area within dark blue, which will not be deformed in this case. We also have over here the possibility to do amplification, and by default, in this case, CATIA decided to add a scale factor of 31. In reality, this should be set 1:1 if you want to see exactly what will be displaced, but that will not allow you to visually see exactly where is that displacement. So usually it's a good idea to leave this at a larger scale, so you're gonna see how that will deform. But now over here, if I will go, and we're gonna see all those points where the software calculated that. So all of these points will be within the dark red section, and they will be heavily deformed. And if I will slowly move my mouse, for example, this will be minus with the last value over there. That will be the value for the displacement. So over here I'm within the 5 range, and we see 5.6 and so on. Over here within the orange, 565 and so on. Over here in the middle, the values will be even higher. Now, if I want to check the maximum values, again, we can go over here. We can click OK. And in this case, we're going to see that the maximum value over here will be for this point over here. And the minimum will be chosen somewhere over here. So this has been the one selected, even though multiple will have the same point. So this will have again the same value, the same displacement. And over here, as we can see, this will be mine. We see 669 over here. So there's that difference between those two. We're also going to take a look at von Mises tension over here. So we're going to see the stress within the material. If I will click on this, this will be the visual representation. And we see over here those values. Now, we also see the mesh in the background. If we have that subdivided into smaller components, we can always go for von Mises, for example, to shading with material. and this will display us that color map over here. We can also change the color map. If I'm gonna double click on this, we can set the number of colors. For example, I can go with 20. We're gonna see how that will be increased, and I can reposition that. And again, we're gonna see this. We have the value over here in newtons, with on square meters over here. If I will jump within solid, we're gonna see over here the same analysis. But the main advantage between soliders is that we're also gonna have the yield strength added over here. So currently over here I added plain carbon steel. Within solid we have a wider variety of materials, and we're gonna see that they will all have different properties. For example, we see the yield strength over here. We see the yield strength for this type of steel or for the other. So this steel, we see the yield strength is a lot higher. So if I will apply this, this will be similar to this, but this is a lot smaller. So this will be almost half of that value. And what I really like within solid is that we can easily see over here where that value will be positioned, so compared to the yield strength of a material. But within CATIA, we don't have exactly a visual representation over here. In fact, we need to go within the material, and over here we're gonna see the yield strength. So this is the value, the default steel within CATIA. We can change that. For example, if you have some specific materials, we can add custom values over here, and those will be taken into account for the analysis. But for example, if I will go with the force over here and I will add one more zero at the end, so this will heavily increase. I will click OK. I need to do the computation again because those will no longer be available since I changed that force. I'm gonna click yes to have those computed. And if I will go again within the von Mises, we're gonna see the value. So initially they were like this, so within the following range of 0.7, and now we're gonna go past that threshold. If you're gonna take a look over here, I added additional information regarding von Mises stress. So why this is important, especially to predict the onset of yielding under complex loading. And this is essential in order to see the overall distortion or shearing that the material undergoes. And if I will zoom over here, we're gonna see the value for steel. So if you're gonna go with 600 megapascal over here, we're gonna see that this will be a very high stress for steel. So usually the vast majority will be between 200 and 400. Like for example, the one that we have over here, this will be 350 megapascals. Now, if I will check the von Mises again, in this case, we're gonna see the values over here. So this will be far beyond that. So currently over here we have 818 megapascals, and that will be far beyond that the material that we added. Even though I went over here for the steel and I increased the yield strength, as we can see over here we have 350. But this is a drawback for CATIA when we do analysis, as we can compare this with SolidWorks. We see over here we also have that added, so we're gonna see the yield strength exactly where this will occur. And we can also have access to a wider material over here. So just for steel, we're gonna see all of those materials. So if I will, for example, change this, we're gonna see that this will only have a yield strength of 282 megapascals. But as we can see, some of those will go beyond that. So depending on that the material that is selected, we can further go for larger values over here. Okay, so this was a general overview regarding this. I'm not gonna stick with SolidWorks for this, since this is mainly intended for CATIA. But overall, I think that the analyses over there are a little bit, let's say, in some case, easier to process, so that not regarding the computational, but in order to see exactly what's happening with within that analysis, and when, where are those points. So the yield strength limit over here, we don't have an exact representation over here, and it is a little bit harder to see. Okay, so I hope you enjoy this kind of content. I will position, before that, let me just check the displacement, because we added one more zero to the force. And initially, and we're gonna see this will be the displacement with this value. So we see in millimeters. Let me just make sure that the value has been properly added. It should have. So you see that the displacement will be 67.1 millimeters in this case. So if I will reapply that, that will be the value for this distributed force. Okay, so I hope you enjoy this kind of content. I will position a similar video over here on the left, and I will also add a subscribe button to the right. So that's it. Thanks for watching.